Once upon a time, there was a mysterious object in space that scientists had been trying to see for years, a black hole. They knew it was there, lurking in the center of the Messier 87 galaxy, but they had never actually seen it. That was until one day, when a team of brilliant scientists managed to capture the first ever image of a black hole. The black hole they spotted was a supermassive one, like many others found in the centers of galaxies. It was so massive that it held hundreds of billions of stars in orbit around it, just like our Sun holds planets in orbit in our solar system. But this black hole was on the more massive end of the scale, cramming in a whopping 6 billion times the mass of our Sun into an area the size of Neptune's orbit. However, despite its massive size, this was not titled as the most massive black hole known to us. That title was actually taken by Ton 618, due to its unbelievable 66 billion times the mass of our Sun. To put that in perspective, if you were to take all the stars in our Milky Way galaxy and condense their matter to create a black hole, you still wouldn't have enough material to match Ton 618's size. Have you ever wondered what would happen if you found yourself near a black hole? These cosmic monsters are made up of an incredible amount of matter, packed tightly together to create a gravitational pull so strong that it is not possible for even light to escape it. Contrary to popular belief, black holes are not roaming monsters in the universe, devouring everything in their path. Even the most massive black hole we know of, Ton 618, still has a whole galaxy of stars orbiting around it without getting sucked in. The process of growing a black hole is actually incredibly difficult. First, you need to get enough material close enough to the black hole for its gravity to start affecting it. With the vastness of the universe and the density of black holes, this is easier said than done. But if you do happen to get too close to a black hole, the gravity increases exponentially, the closer you get. It's like walking up a hill, but the hill becomes steeper with every step you take. And if you were to approach a black hole with your hands first, the pull of gravity at your hands would be so much stronger than at your body that you get stretched out like spaghetti. We refer to this process as spaghettification. We've seen this happening already to stars and clouds of gas when they get too close to a black hole. The approached matter gets spaghettified and then pulled into orbit around the black hole, forming a swirling disk of material. The event horizon is the sphere around the black hole that marks its size. The larger the event horizon, the more massive the black hole. Beyond the event horizon, matter is crushed down into an incredibly small space, known as the singularity. This is the point of no return, where the black hole's gravity is so strong that not even light can escape. If you cross the event horizon, you'll become part of the black hole and contribute to its total mass forevermore. But as we've seen, getting matter to cross the event horizon is what's so difficult about growing black holes. It's not like they're vacuum cleaners, sucking everything in their path. It takes a lot of effort to get anything close enough to a black hole for it to be affected by its gravity. What actually ends up falling into a black hole? The answer lies in the collisions that occur between particles in the disk of material that orbits the black hole. Similar to how a snooker ball transfers its energy to another ball, hydrogen gas atoms collide and transfer energy among themselves. While some collisions will result in an equal exchange of energy, others will result in one particle gaining energy and being pushed further away from the black hole, while the other loses energy and gradually slides down to cross the event horizon and become part of the black hole. This process, where particles collide, exchange energy, and fall into the black hole, takes an incredibly long time, often millions of years just to get a black hole to a size where it can snack on a passing gas cloud that drifts too close. How much amount of matter can a black hole actually take? The amount of matter that can fall into a black hole is limited by several factors, including the speed and temperature of the disk of matter orbiting around it. As particles collide and transfer energy in the disk, they heat up due to friction and emit light. This glow allows us to detect and measure the mass of black holes. However, this glow also creates radiation pressure that prevents more matter from falling into the black hole. If there is too much material in the disk, the radiation pressure increases and pushes material away from the black hole. This creates a delicate balance between the size of the black hole and the quantity of matter in its disk. When a certain threshold is reached, depending on the mass of the black hole, the universe effectively puts the black hole on a diet to prevent it from becoming too gluttonous, and exceeding this limit. How big can black holes get? Ton 618 is an exceptional black hole due to the amount of physics that stands in the way of its growth. Radiation pressure places a limit on how fast a black hole can grow, known to as the Eddington limit. However, there is no theoretical limit to how massive a black hole can become through merging with other black holes. The maximum mass a black hole can achieve through accretion is estimated to be 50 billion solar masses, based on a research paper. When a black hole reaches 50 billion solar masses, the particles in the disk of material orbiting the black hole will never lose enough energy to spiral into the black hole. If there is no disk of material around the black hole, it will be invisible. Ton 618, with an ultramassive black hole of 66 billion solar masses, lies above the estimated maximum limit for a non-spinning black hole. However, since most black holes are spinning, it may still be below its maximum possible mass. To sum up, the implications of the limit on black hole growth are intriguing to contemplate. We may be approaching a point in the history of the universe where black holes can no longer accrete matter and continue to grow, resulting in the eventual fading of quasars as the black holes become less active. In conclusion, it's also possible that there are already ultramassive black holes in existence in the universe, but without the presence of a glowing disk of material orbiting around them, they remain undetectable. There could be such black holes hiding in plain sight, right in our cosmic neighborhood.